In the previous lecture, I left you with a question. And in this lecture, it will be hardly a 5-minute lecture. I'm going to show you how to solve that question that we left in the previous lecture. This is hardly it will take few minutes of yours. So just let me help you out with the question. So the question that I asked was, a thin insulating rod is running from Z equal to minus A to Z equal to plus A, carrying a linear charge density, lambda is equal to K cos pi Z upon A, where K is greater than 0. It was asked what is the leading term in the multipole expansion of the potential. Okay, so step by step I'm doing it. First, whenever a question of multipole expansion is asked, the first thing that you should do is you should try to find what is the total charge. Because if total charge is non-zero, then the leading term would be governed by the potential due to monopole. Okay, so now here I have found that total charge Q can be given by lambda dz. So total charge Q can be given by lambda dz. And you can clearly see that lambda dz would be equivalent to writing K cos pi Z upon A dz from minus 80%. Okay. And cos pi Z upon A dz, this integration would give you A upon pi sine pi Z upon A. And if you write plus A and minus A, this would be sine pi minus pi. So sine minus sine minus pi. So overall, this is 0, this is 0. Overall, it would be 0. So your net total charge would be 0. So your monopole contribution to the potential would be 0. So there would be no such contribution, due to the monopole. So your leading term will not be found by V monopole. Next, you know that next term would be corresponding to the potential due to dipole. So let us first find if there is some dipole moment or not. So what is dipole moment? Dipole moment is integral Z, that is R vector dq. So instead of R, we have Z, and instead of dq, we have lambda dz. For just knowing this, like you can take, I will just explain you. Let's say this is your charge density on the z-axis. This is your origin. So at a distance z, I have taken an element dz, and this element dz contains the volume, contains the charge lambda dz. So it is at a distance z. So your r vector can be written as zk cap, and then what is dq? dq can be written as lambda dz. So, and your lambda happens to be the function of z here itself. So you can see that lambda is a function of z here, and which is given by this. So if you solve this up, you'll find that your p vector would also come out as 0. So this is an easy integration for you. Z cos pi z upon a dz. First integrate cos pi z upon a. So this will give you sine pi z upon a. Then you can find it by integration by parts that your net dipole moment vector would be 0. And instead, it was quite evident also, because see, anyway, if a charge is distributed from minus a to plus a in the form of k cos pi z upon a, the charge density is symmetric with respect to origin. It is quite symmetric with respect to origin, because cos minus z is also equal to cos z. So instead of z, if you replace minus z, you will get cos pi z upon a. So cos pi minus z upon a is equal to cos pi z upon a. So lambda minus z equal to lambda z. So this implies that the linear charge density is symmetrically placed with respect to origin, is symmetric with respect to origin. Or you can say that your origin happens to be a point of symmetry. So if there is a point of symmetry, that is, origin is a point of symmetry for the charge distribution, that the net dipole moment vector has to be 0. So this is something that you can do in your exam very fastly, or otherwise, if you're interested in finding the integration, that also you can. So your p vector comes out to be 0, and total charge is also coming out to be 0. So obviously, one needs to go and check what would be the potential due to quadrupole. So potential due to quadrupole is p2 cos theta divided by 4 pi epsilon naught r cube, and this is minus a to a z square cos pi z upon a dz. This is, I'm leaving to you as an exercise, because this is a integral by parts, and I think you can do it. And you will arrive at this solution, that is 1 upon 4 pi epsilon naught minus 4a square k upon pi square 1 upon 2 r cube 3 cos square theta minus. So overall, in this question, one can see that your total charge was becoming 0 because of the presence of symmetry, that is, origin was symmetric, or you can say the charge distribution is symmetric with respect to origin. So your p vector has to be 0. So obviously your quadrupole moment has to be checked, and in fact you will find that your quadrupole moment potential due to quadrupole would be seen, and one can see that the potential due to quadrupole is a non-zero. So the leading term in the multipole expansion would be governed by the potential due to quadrupole. So this will be a leading term. I hope this lecture has, this lecture has previously done almost 2 to 3 lectures, have given you a good amount of insight in multipole expansion. And I hope it helps all these kind of thoughts or all these kinds of like discussions help you in your examination. If you have certain doubts, kindly let me know. And if there is some lacuna if you see, or if some kind of flaw you see in my understanding or my teaching, kindly let me know that also. I'll be happy to help you out. Till then, take care.